Part 3 of this video series is going to bring together the information in parts 1 and 2. Makes total sense, right? 1 plus 2 is 3 after all. So to start off, I wanted to review the picture we saw at the end of part 1, where we were fitting a gamma, a y-bolt, and a log normal distribution all over the data, the incubation time data from the Bacher study. Now, one of the questions we had there was, well, how could we distinguish between these three curves in terms of saying which one's a better fit to this specific data set? And we're going to start off doing that by discussing how to perform a goodness of fit test for continuous data. Now, the null hypothesis for any such test is that the data comes from the hypothesized distribution y. So in our examples, the hypothesized distributions y are going to be things like a gamma, right, with an appropriate value of r and theta, or a log normal or a y-bold distribution. So in these goodness of fit tests for continuous data, the null is that the hypothesized distribution does provide an accurate fit, and the alternative is that it doesn't. So if you fail to reject the null in this scenario, you can say that the data is consistent with the hypothesized distribution. Now in the last video, we saw how to perform this type of tests where that null distribution was uniform on some symbols 1 through m, right? The trick to converting between this last and the continuous version is that what we're going to do is we're going to choose some cut points C1 through Cm, which partition the range of y into areas of equal probability m, 1 over m, right? This is really the way of kind of taking that continuous distribution which has an infinite number of possible values and boiling it down to ranges which kind of can be associated with each of these numbers 1 through m. After you do that, getting the expected counts for each bin of values, right, is going to be pretty easy. It's just going to be 1 over m times our sample size. Then, to get the observed counts, you simply count the number of observations lying between the successive cut points C1 through Cm, right, and compare those with the expected values. So, to give you an example, let's look at this for the case where m equals 5 and y is a gamma distribution. So we know that the range of y, if y is gamma, is 0 infinity, with really 0 not included, but it doesn't matter since it's continuous. So for our first cut point, we're going to choose C1 so that the probability y is less than or equal to C1, right, really between 0 and C1, is going to be 1/5, which means that C1 is the 20th quantile, or the 0.2 quantile of the gamma distribution with the appropriate parameters involved. Right? Then, for our next cut point, we're going to choose a C2 so that the probability of y being between C1 and C2 is also 1/5, which means that C2 should be the 0.4 quantile, right? So that difference is 0.2. So we can continue on in this way and choose C3 and C4. And at the end of the day, what this ends up looking like is the following curve. So in this curve, the first black line is just the lower bound on the range of the gamma distribution. So this orange line is going to be C1. That's the 20th percentile. The blue line is going to be C2. The green line is C3. And the yellow line is C4. Notice that this doesn't in any way do an equal partition of possible incubation times, but what's equal is the area under the curve between each of these cut points. So if I look at the area under the curve up until C1, that will be 0.2. And similarly, even though it may or may not look like it in this picture, the area under this curve between C1 and C2 is also 0.2. So all of those areas are 0.2. So that means that if I have my 25 observations, which you'll recall was the total number of incubation times in our data set, I'd expect 5 of them to be in each of these intervals, right? So the first interval will be between 0 and the orange line, the blue line, and the green line, etc. Now for the observed counts, we just need to look into our data set and count how many observation times are in between each of these, and then compare those, and away we go. Now before we complete that test in R, I wanted to take a moment to mention the degrees of freedom that we're going to end up with for this test. Now in the uniform case, you might recall that the degrees of freedom was the number of categories minus 1, right? That minus 1 coming from the fact that one of the counts could be determined from the total in the others. However, you might also recall from our last video series that when we're looking at these normal random variables, that the quantities xi minus mu over sigma squared, right? So this is like basically a sum of zi squareds, that this quantity is chi-squared with n degrees of freedom. But if I substitute the mu, right, for x bar, so basically I'm taking an unknown parameter mu and replacing it with its MLE in this case, or some estimator, then I lose a degree of freedom by doing so. In general, this turns out to be a principle that holds for all of these chi-squared tests, so that the typical degrees of freedom is always m minus 1, but then also minus p, where p equals the number of parameters that you had to estimate, right? So in all three of our curve examples with the gamma, Weibull, and log normal, you'll recall that p was equal to 2. So the degrees of freedom for our tests have to be whatever we choose as m minus 1 and then minus an additional 2. I wanted to quickly run through the code that, as I mentioned before, is also posted on Canvas for running these chi-squared tests with continuous distributions. We're going to start off the code just by defining what m is going to be. And I'm going to take m to be 5 because I have 25 observations. So this splits them nicely up into groups of 5. And I'm going to define my bins, so just to be a sequence of values from 0 to 1 that are spaced by 1 over m. So in this case, they're going to be spaced by 0.2. N is just the sample size, the number of observations in my data set. And then I'm using quantile functions to determine those cutoffs, the C1 through C5 in the video, based on the gamma, the bins here, right, for the gamma, the Weibull, or the L norm distribution. So for example, Q gamma with bins as its first argument is going to tell me the cutoffs for the gamma distribution for the 0th, the 20th, the 40th, the 60th, the 80th, and the 100th percentiles with a shape and a scale parameter given by my MLEs. And similarly, the Q Weibull and the QL norm function can be used to get the Weibull and L norm cuts. Now in R, there's a pretty nice and nifty little way to get the observed counts using the histogram function. Histograms naturally tend to take a variable, right, an input variable, and split it up into values based on some predetermined set of breaks. So for example, if I want to cut up my data based on the cut points for the gamma, then I can just set breaks equal to gamma cuts. I don't actually want to see the plot in this case, but what I do want is to get the counts off of that histogram data. So this sort of syntax is useful in achieving that task. We do the same for the Weibull and the log normal, and these are now going to be our observed counts in 3 separate chi-squared goodness of fit tests. Finally, we define our expected counts as just a single list of objects where I'm repeating m times, so that's just going to be 5 repeated 5 times. I'm going to define the chi-squared statistic as a function because I'm going to have to run it 3 times. This is just sort of a little bit of a time saver. So the function is going to take an expected list and an observed list and compute the chi-squared statistic as the sum of the squared deviations divided by the expecteds. And then I'm going to organize my results in a data frame. So the first column of the data frame is just going to tell us which distribution I'm fitting, and the second column is going to tell us what the corresponding chi-squared statistic is. So let's run this code for a moment here. And I get 2 things as an output. First of all, this last line, second to last line here, prints the critical cutoff for the chi-squared test. Notice here I'm using my degrees of freedom as m minus 2 because we fit 2 parameters, minus 1. And the critical cutoff at a 0.05 significance level would be 5.991. If I look at my actual results, notice that all 3 chi-squared values are well below that, so I would fail to reject the null hypothesis and conclude that this data is consistent with any of the 3 distributions. Now there's some people and this really makes sense if you think about it, who say that for a goodness of fit test, you should actually use a much higher significance level. So you should actually you should be wanting to reduce the type 2 error in this case and being okay with a little more type 1 error. Since you, as the user, specified the null distribution, you should have to kind of provide more evidence, or at least be able to reject it more easily in some cases. So let's say instead we use a significance level of 0.2, in which case we would be looking at the 80th quantile of the gamma. Let's see what cutoff that gives us. So the critical cutoff in that case is 3.219. So all three distributions are still below that, and hence all three appear to be consistent with our data. Of course, one obvious issue with the demonstration in the last slide is how do we choose m, right? I chose m equal 5. It seems somewhat reasonable. It split the data nicely up into 5 regions. But why not 6 or 7 or 8 or 10 or 1 or 3 or 4, right? In the ideal world, it wouldn't matter what we choose to be m. I would get the same result. But unfortunately, that's not always the case for the chi-square goodness of fit test. It does depend on what m you choose. For this reason, some prefer the Kolmogorv Smirnov test when performing goodness of fit with continuous distributions. Now, the Kolmogorv Smirnov test, or KS for short, is a test named after two of probability theory's founders, both Russian mathematicians. And it doesn't bin the data into any arbitrary way. What it does instead is it calculates something we call the empirical cumulative distribution function for our data. So you'll recall that the CDF for a random variable x is defined as the function fx of little x, which looks at the probability of your random variable lying below the value of little x. So the empirical does a similar thing, except it just takes, as an argument x, it counts the number of observations which lie below this value and divides it by n. And the Kolmogorov Smirnov test statistic then looks at the maximum difference between your observed empirical CDF and the CDF that you would expect under the null hypothesis. And since pictures speak louder than words, I wanted to show you an example of what this looks like for our incubation time data. So in this graph, the black curve here, it's a step function, right? Because every time I get a new data point, it jumps up a little bit. But that step function is the empirical CDF. So that's our f OBS of x, right? So for example, the smallest incubation time right here was about 1.5, and therefore the first jump that we see occurs at 1.5, and it jumps to the value of 1 over 25, because that's the probability of getting an observation that is less than or equal to this value of x. That continues until we get to our next jump, which is around 2, and then another jump a little after 2, and so on. And the smooth curves here are the fits from the gamma, the Weibull, and the log normal distribution. And once again, we can see that they all give relatively reasonable fits. R has a nice simple function that will perform the KS test for you, and it's called, very mysteriously, ks.test. The two first arguments are the data. So this is the data for which you want an empirical CDF, and then the distribution function you want to fit to that data, and any parameters that are involved in that distribution. So we're going to perform 3 separate Kolmogorov Smirnov tests based on the gamma, the Weibull, and the norm, the L norm function, the log norm. And you can see when we run those 3 tests, so the first one here is for the gamma, for example, the output's relatively simple. Basically, it's performing a hypothesis test that the data is consistent with the given distribution against whether or not it isn't. The D it computes here is that Kolmogorov test statistic, which is the maximum deviation between the empirical and the hypothesized distribution. And it's important to note that the smaller the D, the better in this case, right? That's the opposite of chi-squared, where, well, actually, it's not the opposite of chi-squared. The smaller the chi-squared, the better also. And the p-value here, notice it doesn't give you a critical region, it just gives you a p-value. So you have to do p-value hypothesis testing if you want to use this function. In this case, the p-value is extremely large, and we would fail to reject under any reasonable significance level. Similar results hold for the Weibull and the log normal examples. Notice, however, that actually in this case, the Weibull gives us the smallest value of D, so the smallest absolute deviation. And so in some ways, maybe by the Kolmogorov Smirnov test, the the Weibull distribution may actually be the best fit of the three. And that was actually, I believe, the conclusion of that backer paper at the end of the day. So, I hope you enjoyed these videos. Hope you found them relevant and interesting. I know I said there was going to be a part 4. I'm not sure that's going to happen. I'm not sure what's going to happen. None of us are. But I'll see you again soon enough.